Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over how to explain or describe the, uh, the molecule benzoic acid using both the localized electron model and in addition to that molecular orbital model that describes the delocalized electrons. So let's get into this. So in this problem, we're given benzoic acid. It says use the localized electron model combined with the molecular orbital model to describe the bonding for the molecule benzoic acid, C6H5, C double bond O or COOH. Okay, first thing I want to point out, just as an aside, COOH, anytime you see COOH in a molecule, that indicates that it is in the group of organic molecules known as carboxylic acids. So usually it will end, the name of that will end in oic acid. So that's why if you notice here, we have what is considered the benzene ring. So if I was to cover this up, basically you have benzene. If this was replaced with a hydrogen, right? Then we have benzene. Here you have the C double bond OOH. This is known as a carboxylic acid group. So if you see one of these on your molecule, you know it's a carboxylic acid, and that is why this is known as benzoic acid. So that's just an aside. Okay, so we want to be able to describe this molecule using the localized electron model and the molecular orbital model. You're going to use the localized electron model to describe sigma bonding. That's usually what you use it for, to try to describe benzoic acid using only molecular orbital theory would be way over complicated. I should say overcomplicated, but it's quite complex. So to simplify matters, you can use both to describe your molecule if there's resonance structures involved, or if there's any sort of resonance involved in your molecule. You can use the localized electron model like valence bond theory to describe the sigma bonding, right? That would be like using your sp2, sp3, sp hybridization, and to describe the sigma bonding and the shape. But then when it comes to the pi bonds, you can use molecular orbital theory to describe those. So in this molecule here, I have the Lewis dot structure for benzoic acid. So you can see here that you have the double bonds, and you can see that there's resonance because you can move the double bond. So the pair of electrons in this bond can move and form a double bond there. That would push the electrons in this double bond to form a double bond there, and then these electrons would be pushed there, so they could be switched to the next set of carbons, and so you see that alternating. And then so a lot of times we'll write this down. Where's my marker? A lot of times we'll depict this in this way, where each corner represents a carbon. You don't necessarily have to write in the hydrogens, right? So we have a carbon here, carbon here, carbon here. And then you can draw a circle in there representing that the fact that the double bond is kind of applied to all of these atoms. So not that there's a double bond exactly, it's going to be somewhere in between a double and a single bond, but this kind of shows you that the electrons can move around. Okay, so how do we go ahead and describe this? So using the localized electron bonds or localized electron theory or model, we can depict the sigma bonding for the carbons and the hydrogens. So that's what I have shown here. So each of these carbons is sp2 hybridized, so they have the trigonal planar shape. So they're all trigonal planar. So this is one plane. So this is sp2 hybridized, this is sp2 hybridized, this one, this one. So all the carbons in this ring are sp2 hybridized, and you can see the trigonal planar, and it's the trigonal planar structure or shape that gives the carbon, that gives this ring its six-sided shape, right? So you could see that the triangular structure of this carbon matches with the triangular shape of this carbon here, and they bond this way, and this one bonds this way, so you get that 120-degree angle here, and then you have the 120-degree angle here, and so on, right? So then it forms this six-sided shape here. Okay, so all of these are sigma bonds. So the hydrogen unhybridized s orbital overlaps with the sp2 hybrid orbitals, and so on. So you got the hydrogen here, sigma bonds. So these are all sigma bonds. And so you can describe how these atoms are bonded together by sigma bonds. And all of this is sp2 hybridized. Okay, so again, I want to come back to here. You'll notice here, this double bond, you can be transferred over here. So there's some resonance here as well, right? So what can happen is that the electrons here, right, in this oxygen, right, can move here. The electrons in this bond here between the oxygen and the hydrogen, this bond is fairly weak because of the resonance. So this hydrogen can give up the electrons in the bond. So these electrons can go on to this oxygen as a lone pair. So you end up with 3 lone pairs on this one. This hydrogen pops off as H+. Then one of the lone pairs on here can be pushed and create a double bond between the oxygen and carbon here, thus pushing a pair of electrons in this double bond onto this oxygen, which is going to give this oxygen here a partial negative charge. And then the hydrogen, the plus hydrogen here, the positive hydrogen can then bond to that one. So because of the resonance here, this hydrogen is really weakly tied to that oxygen. Okay, so the bond here between these two oxygens is not going to be exactly a single bond or a double bond. It's going to be somewhere in between a single and double bond because of the delocalization of the electrons. So we have delocalization of electrons here, and we obviously have delocalization of the electrons here. So in order to explain that, we can use molecular orbital model or molecular orbital theory. So in this case, because these are sp2 hybridized, that means that each carbon has one unhybridized p orbital. And so this is all planar molecules. So all of these atoms are in the same plane, and here they are in the plane of the board, right? So that means that the unhybridized p orbital on all of the carbons are sticking out of the board and going into the board. So on top, in front of the board is going to be the top part of your unhybridized p orbitals, and in the behind the board is going to be the bottom part of the unhybridized p orbital. And so because you have those unhybridized p orbitals, they will all interact and combine with each other either destructively or constructively, giving rise to the molecular orbitals. And so because you get molecular orbitals from the atomic orbitals, remember you got six atomic orbitals here, unhybridized p orbitals, those are going to give rise to the pi bonding, right? So because you have 6 unhybridized atomic orbitals on the 6 carbons, that's going to give rise to 6 molecular orbitals. And of course, you would have your molecular orbital energy diagram with the 6 molecular orbitals, and you'd have 6 electrons, so you'd fill in with the 6 electrons, and basically you'd figure out what the bond order of for the pi bonds. So, and then that number of pi bonds would be shared between the carbon atoms. So you'd have 1, 2, 3, 4, 5, 6 bonds holding these 6 electrons together, or 6 carbons together, and that bond order that you would calculate would be shared by the 6 carbons. And so again, you'd have electron density like a donut shape above the ring here, and then you'd have a donut shape behind the ring. If we were to turn this, 90 degrees, if we were to take this this ring here and turn it 90 degrees so it's this way, you would see a donut on top and a donut of electron density on the bottom. Same thing over here, the resonance. I wrote this as sp2 hybridized, and so you could figure out that there would be pi bonding shared between these 2 atoms here, the oxygens and the carbons. So you would have some pi bonding going on here, and so you could add to the sigma bond a certain proportion or certain portion of pi bonding that would be due to the resonance here. So that, in a nutshell, is how you can use the localized electron model to explain the sigma bonding, but then you could use the molecular orbital model to explain the pi bonding. And that's it for this video. I hope this video was helpful. If it was helpful, then by all means, like the video, share the video, hit that like button somewhere down here. Also, make sure that you subscribe to my channel. Do me a solid here. Subscribe to the channel. What are you waiting for? Click that notification bell. When you do that, click all so you can be notified by all the videos I put out. And finally, put a comment down below, right down there in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or a topic you would like me to cover, put that down below. I'd be happy to do that for you. Thanks for joining me, and have a great day.